Is that what section we're on? Okay. All right, good. All right, so we are on 1-4, and we're talking about solving equations. So this is kind of like a puzzle. This is the skill of solving equations for a certain variable is an important skill. It's slightly less important now that we have some other graphing tools that we can use, but it's still kind of important to know how to solve for y, for the value of x. So I don't think we did any of these examples, or maybe we did example 1, but what I want to do with these is we want to solve the equation for y, and then we want to plug in the value of x and find out what the y is when we have that x value. All right, so so let's just kind of plow through a couple of these examples, because I think the best way to talk about this section is really just to kind of jump in there and work through some problems. All right, so number 1, we have 9y minus 4x equals negative 30. I don't think we did this one. All right, so we have 9y minus 4x equals negative 30. So that's an equation, right? We have an equation, we have an x and a y, but right now it's not written in a way where we're solved for y. So we want to get, basically when we say solve for y, that means we want to get y all by itself. We want y equals something. So when they say solve the equation for y, we want y equals da 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 da. Okay, so what we need to do is the same thing we would do if we were solving for x. We need to get everything away from y. We need to get it all by itself. So right now, y is being multiplied by 9 and also subtracted by 4x. So you actually could tackle it either way, but one way is way easier than the other. So what I mean by tackling it both ways is we could first divide everything by 9 to get rid of being multiplied by 9, but we don't actually want to do that. Well, we can, but ideally we want to do something else first, because that leaves a whole bunch of fractions, right? So the other thing that we can do is that we can move the 4x from the left side to the right side of the equation. And we can do that by adding 4x to both sides. All right, so then we end up with 9x equals 4x minus 30. Okay, now we do have to actually divide both sides by 9, but at least we didn't have to move fractions around that were being divided by 9, right? Oops, this should be a y, 9y divided by 9. All right, so then we're left over with y equals 4x minus 30 divided by 9. So this equation here, 9y minus 4x equals negative 30, and y equals 4x minus 30 divided by 9 are the same equation. We've just rewritten them in different formats. So it's important to be able to do this for a couple things. Sometimes we need to be able to say, okay, well, what happens when, I need to know what happens when x is, for this one, we wanted to know when x is 8, but I want to know what happens when x is 8. I want to know what happens when x is 0. I want to know what happens when x is 100. Okay, so if we have it in the second format here, this y equals format, then that's a lot easier to kind of plug in and figure out what our y is versus our original format, because we'll plug out the values in and we're going to have to solve for y every single time. So that's a lot easier to be able to do that. The other reason that it was really critical a few years ago is because all of the graphing tools, so I don't think Sarah or Connor, either one of you have a TI. I can't remember. My brain is jumbled. But if you have a TI 8384 calculator and you want to be able to graph these equations, the way that you graph them, the only way you're able to type them in is y equals whatever. It has to be y equals when you type into those types of calculators. Now, Desmos actually lets you type in any format. And I'm actually going to flip over to Desmos, and we're going to graph our original equation and our new equation, or I mean, they were the same equation, but rewritten in different ways. And you can, this is one way that you can quickly check that you've done a good job of rewriting your equation. Okay, so one of these has Desmos on them. Not that one. This one. There we go. All right. That was some pre-calc there. So if you remember, our original equation was 9y minus 4x equals negative 30. So I'm able to graph that in Desmos and see my graph. This is what I'm saying. The way this is written, you can't write that into a TI calculator. It won't let you. In a TI calculator, you have to write it as the format y equals, and then remember our formula is 4x minus 30 divided by 9. Okay, so then what happened when I graphed these two is you only see the second graph, which is colored black, and not the purple one, but you can turn them on and off. So you can see that they're exactly the same line. If you change the colors. And that's just one check. Okay, then I did a good job of changing my equation around, because my equation shouldn't change. My graph shouldn't change. They should be the same. All I'm doing is moving numbers around. The other benefit to graphing is that we can really easily tell. If you remember the original problem, and I don't know what your homework problems ask you for, but it says find the value of y for the given x. So it asks, what is the y value when x equals 8? So one way that you can do that is to actually use your cursor here and trace along. If I can get it exactly right there. Oh man, it's not gonna let me get there. I might have to zoom in a little. I can't get my cursor to move right. Come on. Seriously? All right, maybe if I just zoom in here. Well, there we go. So when x equals 8, y equals 0.222222222, which actually happens to be 2/9. So that's one possible way to solve for what happens when x equals 8. The other way to solve is to have fun with plugging it back into our equation, right? So when x equals 8, we would plug that into this equation we just solved. So it would be 4 times 8 minus 30 over 9. 4 times 8 is 32 minus 30 is 2/9. And if you do 2/9 as a decimal, it's 0.22222. All right. So this little section is just kind of a practice solving for a specific variable. Let's do a couple more because they do get a little bit more complicated, but nothing you guys can't handle. Does that make sense, what we were doing? Okay. Sarah, you good? Awesome. All right. It's my easy way to erase there. All right, so now we have our next equation. And we're going to more focus on the solving part than the plugging in. I know you guys know how to plug in. So this one is 9y again. The book must really like 9y. 9y plus 6xy equals 30. Okay. So what happens now that we have a y in both terms? We have a y in 9y and we have a y in 6x plus y. But I can't add them together because they're not like terms, right? I can't add 9y and 6xy together because that x in the 6xy. So how are we going to get y by itself? Well, it has to do actually with my favorite property, which is the distributive property, right? And we can actually use it to pull a y out of both of these terms. You could also technically pull a 3 out, but we don't really want to do that. We just want to pull the y out because we're trying to get y by itself. So if we pull y out of 9y, we're left with 9. And if we pull a y out of 6xy, what are we left with? 6x, right? And then that equals 30. So how does that help us? Well, now we have y all by itself, right? And it's times everything in the parentheses here. And it's kind of a weird thing to do. I think it kind of feels weird to do. But I mean, this is basically like y times 3. You know, if we had 3y, we would just divide by 3 to get rid of the 3, right? So we are actually able to divide this by 9 plus 6x. And if we do that, we have to divide this side by 9 plus 6x. But that actually lets us cross off this big crazy thing, and we're left with y equals 30 divided by 9 plus 6x. So this yellow and this green are the same equation. They're just written in two different formats. Okay. Let's see if we throw that up on Desmos really fast. Let's just double check our work. Okay, so I have 9y plus 6xy equals 30. I have to change my graph window so I can see that. And we said that it was y equals 30 divided by 9 plus 6x. I can't see anything, so let me... default zoom. There we go. Oh, that's a pretty graph. All right, so I don't see a red graph anywhere. That's probably good news. If I hide my blue graph, the red graph is right underneath it. So that means I did a good job. Yay, us. All right, have you ever done anything like that before? I think it's a little bit different, so I wanted to make sure I showed one like that. Okay. I think we can skip number 3. It's really similar to number 2. So, but let's tackle number 4, because number 4 is one of those really funky ones that the first time I was like, huh, exactly how do we do that? Okay, so let me clear off my screen. Unless either of you guys really want to see 3. I'll do 3 if you want, but it's pretty similar to 2. So if you felt good with 2, I think you should be able to tackle that. I mean, you don't have to even do 3, but once you get to your homework, I think you should be able to tackle that one. Okay. So number 4 is kind of a crazy one. It's kind of one of those challenge problems. You're not going to see it that very often, but it'll be good for us to go over. Okay. So, and maybe it's not a challenge for you guys. I just think it's a little bit different. So we have 1 over x plus 1 over y equals 1, and they want us to solve it for y. So what we want to do here is we want to think about how can we get y out of the denominator first of all, and then solve for y, because it's really hard when your y is in the denominator to be able to solve for y. We want to somehow move it up to the numerator. And we can't just move it up to the numerator just because we like to. But if we could get it out of the denominator, that's going to help us a whole lot. All right, so our goal whenever you see a y in the denominator that you want to solve for is to get it out of there. So what are our options to get a y out of the denominator? Well, our options are to multiply by something that's going to kind of pull it out. All right, so in this particular case, what we could multiply by is we can multiply this whole thing by x times y. which is the if you remember fractions, like if this was x equals 2 and y equals 3, then their least common multiple is 6, so we will multiply by that. So we're basically multiplying by the least common multiple of x and y. Okay, so we have x and y over there, and if we multiply this side by x and y, we have to multiply this side by x and y. So this is one of those problems that's going to look worse before it gets better. All right, so if we multiply both sides by x and y, then we're going to need to distribute the x and y to each term. All right, so we will have xy times 1 over x plus xy times 1 over y equals xy. So it kind of looks like we got worse, right? But this is where the kind of the magic comes in, right? We get to cross off an x in the numerator and an x in the denominator, and a y in the numerator and a y in the denominator, and we're left with y plus x equals xy. So we still have y's on both sides of the equation. It's not ideal, but at least we don't have any y in the denominator anymore. So now we have to go about the business of solving for y. So the first thing we have to do is get the y's together so that we can get everything else away. So what do I mean by that? Let's subtract y from both sides. So we're left with x equals xy minus y. And let's use our trick of reverse distributing to pull out our y. So we're left with y equals x minus 1 equals x. And then we can divide both sides by x minus 1. So if you solve this, you get y equals x divided by x minus 1. Okay. So that's like the most complicated scenario. So if you got that, if you followed along for that, then you should be able to do most of the problems in 1.4, because really that's kind of the most complicated example of solving for y. Sound good? All right. Awesome. I am going to do a little bit of 1.5, but Connor, I know you need to drop off, so just drop off whenever you can. And if you want to try 1.5, like I'll keep recording it so you can come back and watch that. All right. All right. So 1.5 is, so like we're kind of flying through these sections. I know it's kind of fast, and that's because we're doing a lot of things where we're just making sure we all have the same basis for when we start digging into some other problems. So 1.5 is kind of a fun little section, I think. It's called Use Problem-Solving Strategies and Models. So what we're actually doing is, in 1.4, we were just talking about a bunch of theoretical formulas. In 1.5, we're actually trying to use them to solve problems. Now, this isn't necessarily like word problems, but it's, you know, some real-life applications that we could use. So, so let me pull this over. Into Paint so that we have some things to work on. So the first example is, it says use the formula perimeter equals 2 times the length plus 2 times the width to solve for the missing variable. So that's kind of one of those standard formulas, that the perimeter of a rectangle, right, is 2 times the length plus 2 times the width. That we know. And so what they're saying is, we're going to tell you that the perimeter is 46 inches and that the width is 4 inches, and we want you to figure out the length. All right, so technically what the book wants you to do with this, and I know that there's other ways to solve this. You could just plug it in as is and then solve. Technically what the book wants you to do is to say, all right, I know that this is the standard formula for perimeter, but let me solve it for length being the unknown variable. Okay, so what I mean is I know it's perimeter equals 2 times the length plus 2 times the width. Okay, in this particular case, we don't know what the length is. And again, I know there's other ways to solve this, but we don't know what the length is. So let's go ahead and solve our equation to make length be the independent variable that varies about the perimeter and the width. So that means let's solve for L so that we can plug in any perimeter and width and figure it out quickly. So how would we solve like an actual equation, a real world equation for that? Well, we're just going to do it the same way we solved before, right? We want to get length all by itself. So in order to do that, we have 2 times the length plus 2 times the width. So let's let's move the width component to the other side. So we can say that the perimeter is perimeter minus 2 times the width equals 2 times the length. Or we can even go further and we can say, oh, well, 2 times the length, we'll get rid of our 2 there. The length of a rectangle is the perimeter minus 2 times the width divided by 2. So this formula and this formula are the same thing. They've just been solved for different variables, right? And the reason that the second formula is helpful is that they give us P and W. They give us the perimeter and width. And 6 minus 2 times the width, which is 4. I'm just plugging in what they give me now, okay? All divided by 2. So it's 38 divided by 2, or 19. So that the reason this is helpful is if you're doing like a scientific experiment, sometimes you have to do this. I remember doing this several times in science class, and I've talked to other students. Sometimes you'll have to solve formulas for specific variables because you might need to say, okay, well, the perimeter is staying constant at 46, but my width could vary from 4 inches up to 10 inches. So what happens when my width is 10 inches? Well, instead of kind of redoing the whole equation, we're able to just plug in, oh, well, I know instead of a 4 here, I'll put in 10, and I can solve the equation that way. So that's why we want to be able to do that. Again, I know that there's other ways you could do it, but I just wanted you to know that you can manipulate, basically you're manipulating standard equations to be able to solve for a certain variable. All right. That makes sense, Sarah? Cool. All right, so that's one kind of thing that we want to talk about. The other thing we want to talk about is modeling data. So the second problem says, look at the pattern and write an equation to represent the table that's shown. Okay, so let's look at this. We've got a graph of something. I should probably start over here. So we have some more room to work with here. Okay, so this says, look at the pattern and write an equation to represent the value. So we have an X and a Y, and this is a kind of a nice, easy example for us. So what do we notice? When we go from X equals 0 to X equals 1, it looks like our value of Y increases by 50. Right? And then when we go from X equals 1 to X equals 2, our value increases by 50. And then when we go from X equals 2 to X equals 3, our value increases by 50. So if we want to try to write a pattern, an equation to represent this pattern, we know that when X equals 0, we have some number. well, we kind of have a starting number of 57, right? But when x equals 1, the difference from 0 to 1 is 50. And then from 1 to 2 is 50, and 2 to 3 is 50. So that means that we could write 50 times x, and that would represent the jump. Like, so when x equals 0, that kind of doesn't work, but when x equals 1, we increase by 50, right? When x equals 2, we increase by 50. When x equals 3, we increase by 50 from the previous. I feel like I'm not explaining this very well. I should have started with the other one. But we have to also look at what we start with, right? So we know that for every increase in 1x, we go up by 50. But what do we know the start value is for our equation? What happens when x equals 0? We still have a value of y of 57. So that means we need to start at 57, because when x equals 0, we have a value of 57. So when x equals 1, we have 57 plus 50 more, and we get our 107. And when x equals 2, we get 57 plus 100, which is 157. When x equals 3, we get 57 plus 150, which is 207. So if we wanted to write an equation to represent that, we could write it like this. Okay. Awesome. Yeah, that I didn't explain that as well as I would like, but I think you probably get the general idea. I think that's probably enough examples to get started. What I'm going to have you do, since just you and I'm going to have you go ahead, you and whoever's listening online, we're going to go ahead and do 1.4 and 1.5. So that's the homework that's assigned. But if you come across any problems in 1.4 or 1.5 that I didn't cover, then just bring those to class Monday or next week. And so then on Monday in class, we'll cover 1.6 and 1.7. So we're getting close to wrapping up the section. All right, sounds good, Sarah. Thanks for joining. And I will see you on Monday. Bye, thanks.